The sea around Okinawa was a lattice of wakes and gun smoke, thin trails of bursts, low black puffs rising almost at the waterline. Kamikaze attacks were a geometry of terror, aircraft diving straight and unflinching, pilots not trying to evade but to strike, willing to be the weapon itself. For the radar picket ships stretched beyond the fleet like a string of beads, this was not an abstract test of courage, but a problem of pure physics and time. Before the new fuse, a near miss was only a near miss, spectacular but often futile. A shell bursting a few yards from a wing might scatter metal and flame, yet still fail to stop a determined attacker. Gunners set time fuses, directors tried to solve a moving equation, and men on the bridge fed data into instruments that demanded impossible precision. The math was cruel. Time fuses punished small errors. Contact fuses required impossible hits. The result was a halo of bursts and tracers that looked formidable, but too often let a plane through. A tiny invention overturned that logic. Sailors nicknamed it the funny fuse. The Navy called it VT, for variable time. Put simply, it put a miniature radio in the nose of a shell that could sense when metal was dangerously close. When reflected radio energy spiked, the fuse tripped and the round detonated. Not on a preset clock and not on impact, but precisely when proximity made an airburst most lethal. Almost became enough, because closeness itself became the trigger. You could hear the difference. Old gunnery chiefs said VT bursts had a meteor, more decisive thud than the scatter of time-fused airbursts. Whether that was real or the relief of seeing cause finally follow effect, it mattered little. After the first fights, where attackers simply came apart under clouds of 5-inch fragments, crews learned to trust the new tool. Doctrine shifted. Keep the 5-inch guns hot with proximity fuses and let physics, not hope, blunt the kamikaze threat. The story didn't begin with kamikaze pilots. It began in proving grounds and laboratories, with balloons, wireframe mock-ups, and drone targets over bays. When early tests destroyed target drones with a handful of proximity bursts, the theory crossed into practice. A first wartime success followed soon after, and word spread through the fleet. This fragile little radio works, and when it does, it kills. By late 1944, the implication was unmistakable. Kamikaze attacks compressed the time available to detect vector fighters, aim directors, and lay a pattern of bursts. Any improvement in lethality mattered, because one plane through could mean a burning, crippled ship and men thrown into the water. The VT fuse gave gunners a margin they had never had before. For sailors on picket duty, the wall of fire stopped being a prayer and became, increasingly, a plan. Next, we will open the shell and explain how a vacuum tube radio could ride a spinning round, distinguish real echoes from noise, and detonate at the exact moment that turned a near miss into a kill. Let's open the fuse and listen to how it thinks. Imagine holding a radio in one hand and a mechanical watch in the other, then asking both to survive the inside of an artillery shell that has just been fired. That's the basic engineering trick behind the VT, variable time, or proximity fuse. Squeeze a tiny radio transceiver, a detector that decides that's close enough, and a rugged safety and firing train into a cylindrical nose that will be flung out of a breech at thousands of feet per second and subjected to tens of thousands of times gravity. The miracle is that it worked at all. The story of how it worked is a marriage of simple physics, clever circuits, and brutal mechanical design. Start with the goal. A proximity fuse should do 3 things, and only 3 things. It must remain inert and safe until the shell is fired. It must arm reliably while the shell is in flight. and it must sense a nearby target and detonate the main charge at the moment that maximizes damage. Each of those requirements drove a handful of practical design decisions. The sensing principle is radio reflection. Inside the fuse, a small radio transmitter constantly emits a narrow beam of radio waves forward. Those waves travel until they hit something metallic, an airplane's fuselage, a ship's superstructure, and a portion of the signal bounces back. The fuse's receiver listens for that echo. When the returned energy rises above a threshold, the fuse declares, "Target close," trips the firing circuit, and fires the detonator. That sounds straightforward, but the devil is in the details. To begin with, the fuse's radio had to be tiny and simple. The 1940s vacuum tube technology used in lab radios was fragile, not to mention bulky. Engineers at Johns Hopkins Applied Physics Laboratory and at radio firms developed miniaturized oscillators and amplifier stages, special tubes and circuits that could tolerate shock. The whole assembly had to be potted, braced, and suspended in ways that prevented parts from cracking under the brutal acceleration of being fired. Every solder joint, every lead, every glass envelope had to be tested to survive a launch that literally tried to tear it apart. Spin was another problem. Artillery shells are spin stabilized. Rifling in the gun barrel causes the shell to rotate dozens or hundreds of times per second. A spinning fuse can't simply broadcast and listen in all directions uniformly. The rotating antenna pattern means the echo signal will be amplitude modulated at the spin rate. Designers used that fact to their advantage. A simple rotating or directional antenna produced a pulsed echo each revolution when the beam swept past the target. The fuse electronics use that periodicity to distinguish a true echo from momentary noise. Put simply, a real target produced a periodic ping at the spin frequency, while stray reflections were less likely to show the same clean pattern. Safety and arming were solved by mechanical logic. The fuse had to be absolutely safe in storage and handling. To that end, engineers built in multiple interlocks. An arming mechanism depended on acceleration, the shell's tremendous launch pull, and on centrifugal forces from spin. A rotor or vane would only move into an armed position after the shell had experienced the correct acceleration profile and had spun up. Some designs also required a timed delay so that the fuse could not arm until the projectile was well clear of the firing ship or land battery. The result? A fuse that was effectively blind and inert in peacetime handling, then came alive in flight. Once armed, the little radio transmitter-shot receiver pair had to detect the target reliably. That demanded three things of the electronics: adequate transmitted power, sufficient sensitivity in the receiver, and a threshold detector that triggered the firing device only for plausible echoes. The designers were careful to set thresholds high enough that reflections from rain, sea spray, or deck clutter on friendly ships would not cause premature bursts. At the same time, the circuit had to be sensitive enough to pick up the faint echo from a thin-skinned airplane at a useful kill distance. Why radio rather than other approaches? The options were few. Contact fuses required hitting the plane, rare with a fast, low target. Time fuses required the gunner to estimate where the plane would be, error-prone. Photoelectric or acoustic sensing existed as ideas, but only radio offered a compact, robust sensing front that could work across weather conditions and at the few to tens of yards distance that made the difference between a near miss and an effective airburst. Mechanically, the fuse had to interface to the shell's detonator train. When the radar detector signaled close, the fuse circuitry discharges a capacitor through a triggering device, a vacuum tube thyrotron in many early designs, or a more rugged spark gap in some variants. That initiates a detonator, which in turn sets off a booster, and finally the main charge. The timing from detection to detonation is measured in microseconds. The fire train is designed so that the explosive sequence reliably follows the detect pulse without misfire. Engineers also had to solve practical combat pathologies. A ship's own metalwork could create reflections. If a shell burst too close to the firing ship, it could be dangerous. That's why the fuse design included either a minimum arming distance or logic to ignore near reflections that do not follow the expected echo modulation pattern. Ground clutter, reflections from the sea surface or land, could confuse receivers. Clever circuit design and test data helped statistical filters tell the difference. Testing over ranges, with instrumented drones and with instrumented chicken wire mock-ups, revealed how real echoes looked and allowed designers to tune thresholds and the pulse count logic that would authenticate a valid target echo. A few other engineering wrinkles are worth pointing out because they explain practical uses and limitations. First, the lethal effect of a proximity burst is different from a contact explosion. A contact hit concentrates destructive energy at a single point. A proximity burst disperses fragments in a cloud. Against a fabric-covered plane, a cloud of shrapnel at 10 to 20 yards is devastating. Thin skin and control cables shred, fuel tanks rupture, and the aircraft essentially disintegrates. Against kamikaze attacks, in which aircraft deliberately carried bombs or themselves were the weapon, the proximity burst could destroy airframes before impact, or at the very least shear control surfaces, and set the attacker ablaze so it broke up before hitting critical structure. Second, proximity fuses raised new tactical possibilities. Because a near miss now had lethal effect, gunners could choose engagement patterns that maximize the chance that something deadly lay along the attacker's path. That made coordinated barrages more effective. Layered volumes of airburst grenades now formed lethal barriers rather than pretty curtains of smoke and flame. Third, there were failure modes. A fuse could fail to arm if the acceleration profile was atypical. Manufacturing defects could leave a tube that cracked on launch. Threshold settings could be wrong for a particular environment, leading to premature or delayed bursts. That's why production quality control, rigorous testing, and the decision to mass-produce the design to tight tolerances were as important as the original circuit concept. Finally, build to scale mattered. The early field demonstrations worked with a few dozen test fuses. The real victory was mass production, creating millions of units with identical behavior. That required factories to master new tolerances, to standardize potting compounds and shock mounts, and to qualify tubes and components by the tens of thousands. The industrial solution turned laboratory wizardry into a logistical asset. Put simply, the VT fuse let the shell answer a fundamental question in real time: how near is the target? Rather than relying on a human estimate of time or chance contact. That small change in where the decision happened, moving it from human prediction to electronic proximity sensing, converted a weapon set that had many almosts into one that produced far more enoughs. In the brutal calculus of the Pacific, that difference saved ships and men. Next up, we'll take that circuit and follow it out of the lab into the factory and the fleet. The people who turned a fragile prototype into millions of hardened fuses, the secrecy that surrounded the program, and the first combat moments when the tiny radio brain proved it could be trusted. Imagine a 5-inch shell fired from a destroyer's gun mount. In that instant, the fuse at its nose experiences a brutal punch, 30,000 times the force of gravity trying to tear every joint apart. Vacuum tubes, glass envelopes, wires soldered by hand. Nothing about that sounds survivable. Yet the miracle was that inside the spinning projectile, a tiny radio survived long enough to listen for its echo and act on it. The principle was simple, but execution was anything but. The transmitter sent out a continuous stream of radio waves. If those waves struck metal, a wing, a fuselage, even a propeller blade, they bounced back. The fuse's receiver picked up the echo, and when the returning signal was strong enough, the circuit fired. But to get there, scientists at Johns Hopkins Applied Physics Laboratory had to shrink and toughen radio technology that, until then, lived only on laboratory benches. The men who worked on the project were not frontline sailors or soldiers. They were physicists, engineers, radio men, people who had built televisions and broadcast towers before the war. They were asked to do the impossible: make a miniature radio that could survive being fired from a cannon. They invented new types of vacuum tubes, no bigger than a finger, built with reinforced glass and shock-absorbing mounts. They poured wax and resin around circuits to hold them steady under the crushing launch. Each fuse was a tiny laboratory packed into a steel nose cone. Safety was another problem. A fuse couldn't explode while handled on deck. It had to remain dead until fired, then come alive in flight. The solution came from mechanics as much as electronics. Inside, small rotors and weights responded to the spin of the shell as it left the barrel. Only after the shell had accelerated and spun up to speed would the fuse unlock and begin transmitting. By the time it was fully armed, the projectile was already hundreds of yards from the ship. Even then, engineers worried about false alarms. What if sea spray or rain fooled the fuse into exploding early? What if the ship's own radar pulses or reflections from the water set it off? The answer was in the pattern of the echo. A real aircraft, as the spinning shell swept past it, produced a rhythmic signal, a pulse matching the shell's spin rate. The electronics were designed to recognize that rhythm, to discriminate between random noise and the steady beat of a true target. The tests were nerve-wracking. Early prototypes were fired over Chesapeake Bay at target drones, radio-controlled planes meant to mimic attackers. Many fuses failed, smashing themselves into silence on launch, but enough worked to prove the concept. One memorable trial saw a target drone disintegrate under the fragments of a proximity burst, and the observers, hardened scientists though they were, cheered like schoolboys. From that point, secrecy became absolute. The proximity fuse was judged as vital as radar or even the atomic bomb. The fear was that if Germany or Japan learned how it worked, they could copy it, or worse, develop countermeasures. Orders went out. Never use the fuse over land where unexploded shells could be recovered. For months, it was reserved for naval combat, where duds would sink beyond enemy reach. And then came the first real test in battle. In the Solomons in late 1942, U.S. ships equipped with limited stocks of the new fuses engaged Japanese aircraft. Reports filtered back of enemy planes destroyed by shells that did not score direct hits. Gunners told of tracers meeting attackers a little too wide, only to watch planes stagger, break apart, and fall into the sea. Skepticism gave way to belief. The sailors knew they had something extraordinary, a weapon that turned probability in their favor. By the time kamikaze waves crashed against the fleet at Leyte Gulf and Okinawa, thousands of proximity-fused shells were waiting in magazines. Gun crews no longer had to gamble on perfect timing or impossible accuracy. They simply had to fill the air with metal, and the fuses did the rest. The statistics told the story. Hit probabilities that had hovered in the low single digits now rose tenfold. The tiny radio brain inside each shell had shifted the balance of survival for ships and crews. The invention was not glamorous. It had no heroic pilot, no iconic silhouette. Yet for sailors who watched burning aircraft tumble into the sea short of their decks, it was nothing short of salvation. The kamikazes had bet everything on certainty. The proximity fuse stole that certainty back. The proximity fuse arrived wrapped in secrecy. From the moment laboratory tests began to show promise, the men who ran the program understood a basic truth. Its value would evaporate if the enemy captured a single intact example. That awareness shaped everything: the design choices, the way tests were run, where production happened, and the rules for combat use. In technical terms, it was a fragile triumph. In operational terms, it was a strategic asset. That duality made command decisions urgent and at times ruthless. The fuse could not be allowed to fall into the hands of an enemy who might study it and copy it. So the military did the extraordinary. It restricted use, limited distribution, and enforced a kind of scientific wartime censorship. Proximity fuses were handed out in sealed boxes, allocated sparingly at first to ships operating where shells that failed would sink rather than be recovered, and their deployment was written into strict orders. Use over land was forbidden in many theaters unless commanders judged the risk acceptable. The policy made sense. A doomed fuse recovered intact in enemy hands could give away the trick. Secrecy cut two ways. It insulated the program from sabotage and espionage, but it also placed immense pressure on the engineers and manufacturers. The tiny vacuum tubes, the precision coils, the shock-mounted assemblies were not technology any factory had produced before at the required scale. Turning hand-built prototypes into millions of identical parts demanded manufacturing innovations as breathtaking as the circuit designs themselves. The industrial challenge was monumental. Engineers worked with electronics firms, glassmakers, potting specialists, and assembly lines to create a supply chain that could deliver at wartime pace. Vendors had to qualify new materials and techniques, shock-resistant tube mounts, special sealing compounds, and automated winding machines for minute coils. Quality control was obsessive. A single brittle solder joint could mean a dud and a possible intelligence windfall. Factories were retooled. Inspection staffs trained to new tolerances. Packaging and transport procedures choreographed to keep shipments secure. The country's industrial capacity became an invisible partner in the weapon's success. At the same time, the scientific teams continued to refine the design. Field tests on ranges and overbays revealed quirks, sensitivity to sea clutter, odd echoes from certain hull shapes, and failure modes in extreme cold or humidity. Every problem had to be solved at scale. Engineers adjusted thresholds, changed antenna patterns, hardened glass, and reworked arming sequences. What had been a laboratory miracle became, through iteration and discipline, a rugged, mass-producible piece of ordnance. Combat trials were the crucible. Early uses were cautious and deliberate. Selected ships in the Solomons and Guadalcanal were given limited stocks, and observers recorded each engagement. Reports came back in guarded language. Radio intercepts described planes scattered by unusual bursts. Gunnery logs recorded aircraft shredded at ranges previously thought ineffective. Mariners who had watched attackers carve through curtains of time-fused shells now wrote of aircraft simply coming apart under clouds of fragments. Skepticism among older gunners turned to belief as after-action reports converged. The program's custodians had another worry beyond enemy capture: friendly safety. Ship captains needed to know that a shell would not detonate dangerously close to their own deck, or that scatter would not significantly endanger nearby vessels. That is one reason early issuance prioritized naval use over ground forces. At sea, a dud shell sank and was unlikely to be recovered. Over land, the risk of discovery and reverse engineering was real. Those policies evolved, and commanders weighed risk versus necessity as the war pressed on. When the kamikaze threat surged in late 1944 and 1945, the proximity fuze's role shifted from experimental advantage to frontline necessity. The suicide tactic, pilots deliberately turning aircraft into missiles, presented an unprecedented problem. The attacker would not chance escape, so conventional deterrence that banked on pilot survival ceased to apply. The kamikaze pilot's single certainty, his own flight path, actually made the fuse more effective, not less. A stable track produced a strong, predictable echo. The fuse's radio brain could lock onto that echo and detonate at the optimal lethal radius. Doctrine adapted rapidly. Fleet ordnance officers prioritized proximity-fused rounds for the 5-inch dual-purpose mounts that formed the last reliable protective layer around a ship. Gunnery drills changed. Mounts trained in sustained, overlapping patterns of fire that, with proximity fuses, created lethal volumes rather than a scatter of ineffective bursts. Loading procedures, ammunition stowage, spare parts logistics, all were rethought to keep enough VT rounds available where the kamikaze menace was greatest. At picket stations, where destroyers were the exposed eyes of the fleet, magazines were stocked differently. Crews learned to think in patterns and envelopes, trusting that a cloud of well-placed proximity bursts would do the heavy work. The psychological impact was immediate. Sailors who had watched helplessly as attackers plowed through their defensive flank began to feel a practical counterforce. Reports from picket ships describe moments where stunned air crews, both American and British, watched kamikaze aircraft simply fall apart at ranges that just weeks earlier would have seemed impotent. The fuse did not make every engagement a victory, but it changed the odds enough to transform tactics and morale. Kamikaze tactics themselves responded. Enemy planners sought to mass attacks or to create distractions that pulled fighter cover away. They experimented with low-level approaches at sun angles meant to blind radars. Yet the fuse's physics was blunt and indifferent. When shells carrying proximity devices detonated in the path of an incoming plane, the result was often immediate and irreversible. Where the kamikaze had once counted on certainty, he now faced an invisible sensor that refused to wait for perfect aim. That said, the fuse was not a magic bullet. Supply constraints, manufacturing defects, and environmental failure modes meant that not every round functioned. Poorly maintained guns, mismatched training, and chaotic engagements could blunt its advantage. Nonetheless, aggregated across the fleet and through successive engagements, the proximity fuse's statistical improvement in probability of kill translated into ships surviving strikes they once would not have. Commanders revised tactics and redeployed resources on that basis. Behind these tactical changes was an odd alliance. Laboratories and machine shops, rear echelon scientists and frontline sailors, secret orders, and open-deck courage. The program's success was the product of engineering under fire and production under pressure. When the kamikaze waves tapered and the Pacific theater moved toward its end, it became clear that the proximity fuse had played an outsized role, not by ending the kamikaze threat alone, but by buying time, boosting morale, and forcing adaptations that compounded across campaigns. In the next block, we will step into the picket ship's world at Okinawa, the radar plot, the fighter director's voice, the mount captain's commands, and the moment when a stream of 5-inch VT bursts met an attacking kamikaze and changed the fate of a ship and crew. Dawn is a thin blade over the horizon. The sea is glass with a faint, oily sheen. On the destroyer's bridge, the radar plot is a cluster of green blips and numbers. The fighter director, young, voice steady, reads out bearings into the net. Bogey, bearing 080, range 45. In the Combat Information Center, the plotters curse softly as a helicopter voice confirms a low, fast return that looks wrong for a weather echo. This ship is alone on station, a single bead on a string whose other beads are miles away. Here, the fleet's safety is fragile and local. Outside, lookouts squint at the sky and the horizon. The crew is exhausted. Picket duty is a long, repetitive vigil. Yet everyone snaps to a higher alert when that voice comes over the net. The captain orders general quarters. Deck plates shake as men run into stations. The ready-use lockers open at the gun mounts. Loaders click rounds in place. The 5-inch director locks a problem in space and begins to slew. From the forward mount, the gun captain calls the solution. Director on. Local control if necessary. Prepare. VT. A loader snaps around into the breach. The shell clunks. The rammer pulls back. The muzzle flashes when the mount breathes fire, and the shell leaves with a screaming metallic bark. The ocean flashes where it disappears. The director tracks, corrects, and calls lead. Around the ship, other mounts join, laying down overlapping beaten zones. The television of radar shows a streak becoming brighter, closing faster than expected. Voice traffic is clipped and efficient. Fighters are vectored if available. But this is the last ring of defense. Fighters are often too far to arrive before impact. The gun crews must act. They do what trained men do: pattern, not perfect aim; saturation, not precision. Then the bursts begin. The 5-inch shells do not simply blossom at fixed times. Some of them have the tiny radios in their noses. As the attacking plane slices through the fragments, a few shells register the echo and detonate at the optimal radius. The air becomes a thunder of meteor bangs, each explosion shrouded in spray and vapor from the sea and the plane's skin. From the deck, it is brutal and immediate. Fragments flash through the air like menacing silver hail. A plane's wing shears, or a canopy pops outward in a blossom of fire. Sometimes the attacker catches a burst and breaks into flame. Sometimes the fuselage snaps and pours out the pilot's last, black smoke. The ship rocks as the wake and concussion pass. In some cases, the plane, crippled, slides into the waves a few hundred yards short of the hull. Men who have seen dozens of these encounters use the same word: clean. The difference between what used to happen and what happens now is visible in the way strikes end. No slow, stubborn impact, but sudden, catastrophic disintegration. On the CIC chalkboard, the gunnery officer tallies results. A month earlier, similar raids ended with planes through the screen, some striking ships and setting fires that took hours to wrestle under control. Tonight, 3 attackers are engaged. 2 go down in clouds of material before they threaten the ship. The third gets a glancing hit on a stack, but is unable to steer to a full-on impact. The tally shows lives and hulls preserved by inches. That is one engagement. Multiply that trust by dozens of picket ships facing waves of attackers over weeks, and the pattern becomes clear. Analysis after the fact. When officers stitched together logs, pilot reports, and battle damage assessments, showed proximity-fused 5-inch fire changed several variables at once. First, effective engagement range increased. Time fuses demanded near-perfect timing to place fragments in the path of a diving plane. Proximity fuses converted near misses into lethals. Where previously a shell burst 5 yards short of a wing might have been merely cosmetic, now it shredded control surfaces, severed cables, and ruptured tanks. A larger lethal envelope meant more kills per salvo and fewer opportunities for a determined attacker to adjust in the last second. Second, confidence in layered defense rose. Fighter direction remained the best defense, but when fighters were vectored out or overwhelmed, the 5-inch batteries with VT became the last reliable layer. Destroyer crews reported an increase in breakups before ships were struck. That translated into less frequent catastrophic damage to major units, less loss of propulsion, fewer magazine fires, fewer ships dead in the water. Third, the nature of damage shifted. Where kamikaze strikes once left long scars of burning steel and secondary detonations from bombs carried in planes, proximity bursts tended to break attackers apart before they could strike hardened, critical systems. That reduced the incidence of fatal hits and lowered crew casualties in many engagements. Fourth, the psychological effect compounded tactically. Sailors saw planes disintegrate at ranges that earlier would have been ineffective. That reinforced doctrinal changes. Allocate VT rounds to forward batteries and picket ships. Prioritize 5-inch mounts for sustaining fire patterns, and adjust ammunition logistics accordingly. Commanders began to staff picket stations with an eye to keeping those guns supplied. Statistical summaries of the period, drawn from after-action reports and fleet logs, do not claim immunity from kamikaze tactics, but do show marked improvements in survivability, where proximity fuses were used in force. Units employing VT-loaded 5-inch guns reported higher numbers of attackers neutralized before impact, and a corresponding drop in ships put out of action by single-strike events. Importantly, these gains were not merely technical. They allowed commanders to buy time for fighters to reach battle, time to steer damaged ships to safer waters, time to extinguish fires before they reached magazines. But there were caveats. Not every round functioned. Not every mount was properly trained. In chaotic mass attacks, some aircraft still got through, and the enemy adapted in other ways. Waiting tactics, flying at confusing sun angles, massing waves to saturate radar and fighters. The VT fuse did not end the kamikaze threat, but it tilted a brutal risk-reward equation. Where kamikazes had once relied on the near certainty of impact when they broke through, they now faced a sensor that turned geometry into danger. The result was fewer catastrophic hits, lower casualties, and ships that could survive to fight another day. In the broader campaign, those saved days added up. Ships kept station. Logistics stayed intact. Invasion support continued with fewer interruptions. The fuse did not win Okinawa by itself, but it was one of the technologies that made the fleet resilient in the face of suicidal tactics. The stage was set for doctrine and production. To scale the effect up, allocating fuses, training crews, and optimizing tactics so that the small radio brain in 100,000 shells could be multiplied into a fleet-wide defense. The miracle of the fuse was not only its design, but its numbers. A weapon that worked only in prototypes or laboratory batches would have meant nothing on the vast Pacific front. What mattered was scale. Tens of thousands of rounds available for every fleet action, magazines stocked and replenished across half the world. The war was as much about supply chains as it was about ideas, and the proximity fuse became a supreme example of both. Factories across America retooled to build the device. Electronics firms that had once made consumer radios now produced miniaturized vacuum tubes by the crate. Glass plants turned out envelopes hardened for shock. Chemical companies supplied the potting compounds that stabilized circuits against the brutal acceleration of gunfire. Women who had built phonographs on assembly lines now soldered fine wires onto coils the size of a thumbnail. Every fuse represented dozens of careful hands, each component tested, each joint inspected. Quality control was obsessive. Inspectors dropped prototypes down steel tubes to simulate the impact of firing. Test ranges consumed thousands of rounds to verify that the statistics matched requirements. Not perfection, but reliability at a level the Navy could trust. The result was a pipeline that moved from design benches to shipping crates at a tempo the enemy never guessed was possible. Secrecy never relaxed. Production lines were compartmentalized. Workers often did not know what the finished device was for. Military couriers delivered finished fuses to depots under guard. Even in the field, shells were handled with a new layer of caution. Some labeled only with cryptic markings, their true nature known to a handful of officers. And then came the distribution problem. A fuse was no use if it sat in a crate stateside. The Navy built an entire logistical web to feed the front with VT-loaded shells. Cargo ships carried them across the Panama Canal, through San Francisco, Pearl Harbor, and Ulithi, into the forward magazines of destroyers and cruisers. At every step, commanders faced choices. Which units received priority? Should picket destroyers, exposed and vulnerable, get first allotments, or should carriers, the heart of the fleet, be stocked first? In practice, the answer was both, but weighted by danger. At Okinawa, some destroyers reported firing hundreds of proximity rounds in a single day. That volume was sustainable only because the factories back home poured out replacements without pause. It was a symphony of industry. Circuits in New Jersey, glass in Ohio, powder in Illinois, final assembly in Maryland, all converging on a single nose cone fitted to a 5-inch shell that might end its life in a cloud of fragments over the East China Sea. The numbers told their own story. Analysis after the war showed that a destroyer armed with VT shells could expect to bring down roughly 3 times as many attackers as one relying solely on timed fuses. At Okinawa, where hundreds of kamikazes attacked daily, that translated into dozens of ships saved from certain destruction. A statistical weapon, invisible in photographs, but present in survival rates. Gunnery officers noticed another effect: fewer wasted rounds. Where once dozens of shells had to be fired to create a near miss, now a smaller number of bursts were effective. That economy mattered in long fights when magazines ran low. Crews learned to trust the fuse enough to fire fewer, better-placed patterns, confident that close enough would do the work. Historians later debated the exact figures. Some argued the fuse improved effectiveness 5-fold. Others suggested the gain was smaller but still decisive. In truth, the numbers varied by ship, by crew, by circumstance. But across thousands of engagements, the pattern was unmistakable. Proximity fire multiplied the lethality of the fleet's guns, and in doing so, it blunted the kamikaze campaign at its height. For the men on the water, the statistics were less important than the sensation of survival. Sailors who had once watched attackers hit with grim inevitability now saw planes fall short in flames. Officers who wrote casualty lists saw them shrink. Ships that should have been on the bottom made it back to Ulithi, scarred but afloat. Behind each of those moments was a supply line running back across the Pacific to American factories, and behind the factories a community of scientists and workers who would never stand on a deck under fire, but whose inventions and labor meant that deck still existed. The proximity fuse was more than a device. It was a compact fusion of science, secrecy, and industry, turned outward into survival. In Tokyo, the planners had placed their faith in arithmetic. If one aircraft loaded with fuel and explosives could sink a destroyer, and if 10 could disable a carrier, then 1,000, sacrificed without hesitation, could halt an invasion. It was cold mathematics of desperation. By late 1944, the Imperial Navy had no illusions about defeating America in a fleet battle. They hoped only to make the cost so high that the enemy might reconsider. At first, the numbers seemed to justify the gamble. Off Leyte Gulf, kamikaze strikes tore into American decks, burning flight lines, killing men, leaving carriers smoking and destroyers sinking. Reports filtered back that suicide tactics worked better than torpedoes or bombs. Commanders spoke of sure hits and certainty, and young pilots believed that their deaths would be efficient currency against an overwhelming enemy. But as the months passed, certainty crumbled. Pilots reported that the curtain of flak ahead of them had changed. Where once they had seen bursts bloom too high or too wide, now explosions tracked their wings with uncanny accuracy. They spoke of planes shredded before they reached the target, of fireballs that blossomed in the sky instead of on the enemy's decks. In training camps on Kyushu, veterans who returned from failed strikes tried to describe it. They said the Americans had developed self-aiming shells, fire that seemed to know where a plane would be, not where it had been. The phrase "magic bullets" appeared in diaries. A few thought it was radar-directed gunnery. Others suspected some new kind of time fuse. None guessed the truth, that each shell carried a miniature radar of its own. The effect on morale was subtle but corrosive. The kamikaze program relied on absolute faith that a pilot's sacrifice would not be wasted. When whispers spread that half of all attackers were now cut down before reaching their targets, faith began to erode. One pilot wrote in his farewell note that he no longer feared death, but he dreaded the thought of becoming smoke in the sky without ever touching an enemy ship. Another recalled seeing his comrade's plane burst apart mid-dive, shredded by invisible fragments, and thinking, "Even our deaths are being denied to us." In staff rooms, officers tried to adapt. They ordered mass waves, hoping to saturate American defenses. They directed low-level approaches to confuse radar. They experimented with flying at sun angles or weaving in at high speed. But none of these tricks changed the simple physics of a proximity burst. The faster the plane closed, the stronger the echo, the more stable its dive path, the easier the fuse's tiny brain could lock on. Tactics that once promised a kind of terrible inevitability now yielded diminishing returns. The Americans, by contrast, became more confident. Destroyers on radar picket duty knew they would take losses, but they also knew their 5-inch guns could blunt the edge. Carriers operated with less fear that a single pilot might end their mission. The kamikaze campaign, conceived as a weapon of certainty, became another arena of attrition, a contest Japan could not win. One Japanese officer, captured late in the war, reportedly shook his head when told about the proximity fuse. "So small?" he asked, incredulous that a tiny circuit could undo thousands of pilots' sacrifices. In that disbelief lay the essence of the technological gap. Japan had trained men to die. America had built machines to multiply life. The irony was cruel. Kamikaze tactics had been born from arithmetic. So many planes for so many ships. The proximity fuse broke that arithmetic. It made every attacking plane less likely to reach its mark, every sacrifice less efficient, every loss more futile. It did not end the campaign, but it bled its power until it became another tragic chapter in a war already full of them. In the next block, we will step back to examine the strategic balance, how proximity fuses, combined with radar, carriers, and industrial output, became part of the broader technological web that tilted the Pacific War irrevocably against Japan. The proximity fuse was never alone. It arrived into a battlefield already transformed by technology. Radar told ships where the enemy was long before human eyes could. Fighter direction networks turned carriers into mobile fortresses. The industrial machine behind it all poured steel and fuel into the Pacific faster than any opponent could imagine. But the fuse added something unique. It made every gun on every ship more lethal than the enemy expected. Think of it as a multiplier. Radar gave early warning, but without the fuse, gunfire was still a matter of prediction. Carriers could launch fighters, but no fleet ever had enough to stop every attack. The fuse filled the gap between information and firepower. It meant that the curtain of flak surrounding a task force was no longer symbolic. It was deadly. In Washington, strategists noticed. Reports came back that ships armed with proximity-fused ammunition were surviving encounters that had crippled earlier operations. Casualty rates shifted downward. Task forces stayed operational longer. Logistics lines remained intact. A weapon no bigger than a man's fist was quietly reshaping campaign outcomes. Japanese leaders never fully grasped why their pilots were failing in greater numbers. They saw only that missions which once produced burning American decks now ended in wreckage falling into the sea short of the target. For every Japanese innovation, the Allies had a counter. But the proximity fuse was different. It was invisible, unanswerable, a ghostly hand extending the reach of every gunner. The strategic effect was simple but profound. The Kamikaze campaign, meant to bleed the fleet dry, became one more test the fleet could endure. The invincible certainty that Japan hoped to project dissolved into statistics that grew worse with every week. And statistics, in the end, are the language of war. By the summer of 1945, the proximity fuse had become part of a web of systems that made American fleets not only powerful, but resilient. Attacks that should have inflicted crippling losses instead caused damage that was absorbed, repaired, and overcome. The result was a fleet that pressed closer to Japan, undeterred. A small radio brain inside a shell had done what entire squadrons of pilots could not. It shifted the balance of the Pacific War. By the summer of 1945, the Pacific had become a proving ground for endurance. Kamikaze raids still came in waves, sometimes dozens of planes, sometimes only a handful. Each one was deadly serious. Each one carried the possibility of ending a ship's story in fire and twisted steel. Yet the fleet pressed closer and closer to Japan. Carriers operated almost at will. Bombardments struck the home islands, and radar pickets extended a protective shield that no longer cracked as often as it once had. On the decks, sailors noticed something else. They trusted their guns more. A destroyer's 5-inch battery, once seen as a last resort, became a weapon men believed in. The sound of VT bursts was reassurance, not just noise. Crews spoke of the difference in the air, how proximity fire seemed to paint the sky with fragments rather than leave holes between bursts. The invisible shift in mathematics translated into very visible survival. Commanders weighed what all this meant for the future. Operation Downfall, the projected invasion of Japan, loomed on planning tables. Staff officers calculated that kamikaze losses could reach staggering levels once American forces closed in on Kyushu and Honshu. Without the proximity fuse, those estimates bordered on catastrophic. Thousands of ships damaged, perhaps hundreds sunk, tens of thousands of sailors lost. With the fuse in the magazines, the figures, while still grim, tilted toward survivable. It was not optimism. It was arithmetic again, only now arithmetic tilted in the Allies' favor. The Japanese, desperate, kept experimenting. They trained new pilots, prepared rocket-powered gliders, even conceived of piloted torpedoes. Yet none of it solved the same problem. American defenses were killing more attackers before impact than the planners had imagined possible. Reports of wasted sacrifice spread quietly among pilots. A tactic meant to guarantee destruction had become a gamble with terrible odds. When the atomic bombs fell and Japan surrendered, many technologies were credited with shaping the outcome. The submarine campaign that strangled supply, the carrier task forces that struck across oceans, radar that gave vision at night and through storms. The proximity fuse rarely made the headlines. Its work was quiet, statistical, spread across thousands of shells and dozens of engagements. But in the war rooms, analysts recognized it for what it was. One of the decisive tools that blunted the edge of Japan's last weapon. After the war, scientists reflected on what they had built. The fuse was tiny, almost humble in appearance, but it had compressed the power of an entire radar set into the nose of a shell. It showed that electronics could ride into battle at the speed of artillery, could survive impossible forces, and could change the equation of survival. Engineers who once doubted vacuum tubes could last a single shot now looked at crates of fuses that had traveled across oceans, worked in rain and salt, and helped hold the line in the most desperate battles of the Pacific. Sailors, too, carried memories of it. Veterans described the bursts that saved their ships, the strange comfort of hearing shells explode at just the right moment. They rarely spoke of circuits or physics. They remembered the sight of a plane breaking apart before it could reach their decks, and they remembered the relief that followed. For them, the proximity fuse was not an invention. It was survival. The story did not end in 1945. The logic of the fuse carried forward. Post-war missiles, air defense systems, and radar-guided weapons all drew on the same principle. Take the burden off human guesswork and let the weapon decide when it is close enough. In that sense, the tiny radio brain in a wartime shell was a preview of the modern battlefield. The war ended, and with it, the urgent secrecy that had surrounded the proximity fuse. Factories shut down production lines. Scientists returned to universities and companies. Sailors came home to families. For many, the tiny device was just another part of the flood of wartime technology, filed away alongside radar, jet engines, and the atomic bomb. Yet, within military circles, its reputation was different. Those who had watched its performance knew it had quietly saved thousands of lives and hundreds of ships. Its legacy was twofold. On the one hand, it demonstrated what electronics could do in combat. Until then, many officers still thought of war in terms of steel and powder, not circuits and signals. The fuse proved that a radio set could survive the harshest environments, make decisions in fractions of a second, and multiply the lethality of existing weapons without changing the weapons themselves. On the other hand, it reshaped expectations. If one tiny sensor in a shell could change a campaign, what might larger, more sophisticated electronics do when integrated into missiles, aircraft, and ships? During the early Cold War, the logic of the proximity fuse reappeared in new guises. Surface-to-air missiles carried seekers that echoed its principles. Anti-aircraft guns were paired with radar directors that turned whole batteries into scaled-up versions of the fuse's tiny brain. Naval doctrines now assumed that the last line of defense would be electronic, not human guesswork. In every case, the lesson was the same. Give the weapon itself the ability to decide when it is close enough to kill. For veterans, the memory was more personal. They recalled the difference between battles fought before and after the fuse arrived. Some spoke of the hollow despair of watching kamikazes come through curtain after curtain of fire, knowing too many would get through. Then they described the relief when bursts finally began to matter, when explosions tore attackers from the sky before they could strike. To them, the fuse was not theory, not even technology. It was the difference between writing letters to widows and writing orders for the next watch. The Japanese, too, remembered. In post-war interviews, pilots and officers spoke of the sudden change in American gunfire, of attacks that seemed doomed before they even began their dives. They could not name the invention, but they felt its effect. Their certainty turned to dread. Their arithmetic no longer added up. The proximity fuse had fought a psychological battle as well as a physical one, and in both it had won. Today, the device sits quietly in museums, often overlooked by visitors drawn to bigger artifacts. A small nose cone, a few fragile tubes, a coil of wire. Nothing about it suggests drama. Yet in those circuits lay one of the most decisive edges of the Pacific War. It was proof that science could be miniaturized, ruggedized, and turned into survival on the grandest scale. It was a reminder that war is not just fought by those who carry rifles or man the guns, but also by those who solder wires, calibrate circuits, and imagine new ways to solve impossible problems. The proximity fuse never had a famous pilot, never bore a name like Mustang or Sherman, never carried the glamour of a carrier or a battleship. But for the men whose ships were spared, and for the commanders who saw the fleet survive storms of suicide planes, it was as important as any headline weapon of the war. Its true monument is not in stone or metal. It is in the ships that came home, the sailors who lived, and the lesson that even the smallest invention can change the course of history.